We often talk about trying to emulate nature, but how hard is that to literally do? Well, I'm actually very privileged to be joined in the first part of the show by Joaquin Ruiz and John Adams, Director and Deputy Director of Biosphere 2, where they've done exactly that in the Arizona desert. But first, I want to remind you that we want your engagement, we want your questions and comments and feedback. So make sure that you're doing that either via the comments section on the website that you're watching this on, or in the comments section on YouTube, or by joining the conversation using hashtag ThinkDiff on social media. So get those questions in. We want to challenge Joaquin and John as much as possible. But first, Joaquin, I want to start with you. The starting point of this Biosphere 2 story is kind of a slightly sort of sci-fi, wacky 1980s experiment where there was this design to put people under this dome-like structure that we've created, was created in the 1980s, and for them to live there uninterfered with for 2 years. Can you just set the context for what that was all about?
Well, let me just say it would be the best example of think diff. So basically, there were these folks. They included some very distinguished scientists. As I said yesterday at the event, they were three free thinkers. I mean, really people that thought very differently about how we could do things in a way that had not done before. And what they did for a few years is that they used to have these meetings around the world in which they would think about how the ocean operated and how the deserts operated and how all this stuff worked together to make the Earth what it is today, or what it has been for billions of years. And after doing that for many years, they decided that it was too difficult to understand the Earth as we know it just by observing the Earth and analyzing the Earth, because the variables are too complex. So they decided to build this thing called Biosphere 2, Biosphere 1 being the Earth, that in principle would control itself just like the Earth does. So there would be no need to bring in mass or take out mass, but only energy. And that the ecology of the system would control the atmosphere of the system just like the Earth does. And when they were finished with this thing, they also decided to put people in it. And the idea would be that if you want to live in another planet, you need to have something like Biosphere 2 or something like the space station, something that controls itself. And they just went out to build it. So the engineering is extraordinary. They invented the frame that is so beautiful. The whole thing is sealed with stainless steel. I mean, this is like 3 football fields, and there's stainless steel underneath it. So
how large is it?
Well, he knows the numbers way better than I do.
So the structure's 1.27 hectares in size, or a little over 3 acres is the footprint. Its tallest point is about 28 meters. That's the rainforest. And so from a volume perspective, it's hard to put it in context, but if you think about it in the sense that it's about 84 Olympic-sized pools, as sort of the volume inside. But they, as Joaquin mentioned, they achieved a remarkable seal and engineering feat. It only loses 10% of that volume when it was originally designed to the outside atmosphere. So that's more tightly sealed than like the International Space Station. So they could trace where every molecule would go and how that molecule interacted with others in the system, which was really unique.
And of course, the experiment of sticking a group of people inside there for a period of time didn't really work.
Right.
Tell us a little bit about that.
Sure, but let me just say that the biosphere really also, in addition to trying to represent nature, is a representation of what you want to do with a circular economy, right? Because everything in there, you start with a point, and everything was recycled. So they were going to grow food and then use whatever was left over from the food to compost the rest of it. The water was being recycled. Everything was being recycled. The air was being recycled. No air was being pumped in there. So it was a remarkable sort of ideas and remarkable feat of engineering. But a few things did not work, even though these people put a lot of money and a lot of energy into the creation of the biosphere. In those days, they didn't understand how soils worked very well. We actually don't understand how most things work very well in nature. We don't really understand why it rains in detail. So the soils, they didn't understand the soils, and they sucked up all the oxygen. So the oxygen concentration in the atmosphere was low. The CO2 was all whacked out. Anyway, all the gases in the atmosphere were wrong. And these folks also had a hard time growing food. So they could have the minerals that they needed, but they didn't have the calories that they needed. So then all these folks, there were 8 people in there, and John knows way more about this because he's been at Biosphere longer, so you may want to just talk about what happened then.
Yeah, no, so, we look at these different social experiments, whether they're ones that have been done by the major space agencies around the world, and the biggest challenge they have is how do you assemble a team? And how do you get that team to work together? And what they had hoped with Biosphere is that most of these teams, when we think about NASA or the Chinese or the Russian space agencies, they're typically in a really sort of small, confined space. They built Biosphere as large as they did to hopefully offset those very well documented social and psychological challenges. And one of the Biosphereans told me that the only thing that the size of the facility did was delay the onset of those very typical, very well documented social and psychological challenges by about 6 months. So the group couldn't get along. There was big debates on how things should be done or should not be done. As Joaquin had mentioned, oxygen got down. So oxygen outside is 21%. It dropped down to about 14.2%. So there was a medical doctor who was part of a team who his cognitive abilities started to be impaired. And they ultimately had to make a decision that they needed to add oxygen in for the safety of the folks. And also, although they produced quite a bit of food, from a calorie standpoint, it just wasn't enough for all 8 of them. So you're having to work really hard, you don't have a lot of oxygen, you can't get along with your folks, and you're not getting the nutritional needs that you require on a daily basis.
Makes some people quite grumpy.
Well, it made them really grumpy. That's the point of it. And so it was a real challenge. But it was an incredible feat. No one had ever done anything like this. I mean, we think about big science initiatives. Right here in Europe, you look at the Hadron Collider, multinational, many different disciplines get together. What are the fundamental building blocks? Conversely, the University of Arizona is really well known for building the largest, most sophisticated telescope mirrors. We deploy them into space on the remote mountaintops, so we're trying to look to the ends of the universe. We've never created an equivalent tool to understand Earth systems. And as much as we romanticize about traveling into space, that's a really long ways away for us. And so it's here on Earth that we need to understand those systems and how our resources are going to be impacted. And Biosphere is one tool that gives us greater insight into that.
I love that you earlier referred to, I guess, someone who works at Biosphere as a bioseverian or something. Yes, that's great. There's five different climates under this structure. Right. Can you just remind me very quickly what the 5 are? There's a rainforest, an ocean, a desert.
Yep. So what we've got, so originally it was set up, so on the northern end of the structure, the tallest point, you have a system was modeled after an equatorial rainforest, mostly species from in South America. And then you have a coral reef, a Caribbean reef environment, a subtropical savanna. Working your way further south, we actually have a mangrove system. So all 3 species of mangroves that you'd find in North America, red, black, and white mangroves, are included in this. And then on the far end, you have what we call a coastal fog desert. So if you were to travel from the southern part of the U.S. down into Mexico, on the Baja Peninsula, the type of vegetation that you would encounter is represented here. And then the last space was an area that they set up exclusively for agricultural practices.
Great. So, and actually, how are those areas like sort of separated in some way? How do you create such? It's one thing to create an environment that under a dome structure and a sealed steel structure that's like the Earth. There's another thing to create 5.
Right. Well, again, the systems that they chose were all, if you sort of generally think about their climate, they're sort of tropical or subtropical in nature. So there's a little bit of overlap and spillover. So there didn't have to be exact delineation. But also what you can't see underneath is this sort of large system that supports the facility itself. And they refer to that as a technosphere. So it still requires quite a bit of mechanical devices to be able to support. So to be able to create rain, control the temperature, to move water and air around the system, there is still a significant mechanical component. It's those systems that help to allow us to create a rainforest or an ocean or a savanna or a marsh or a desert.
So when just to make it clear, when the thing was with the biospheres in there, it was in fact everything was open.
Yeah.
But right now, the experiments that we've put partitions. So the ocean is partitioned from the rainforest, and so on. So you can do that kind of stuff with a facility. You can either partition it or you can have it open, and it depends on the kinds of experiments that you're interested in doing.
And that kind of leads us on to the next phase of this story. That the 1980s wacky experiment may have failed, but obviously you're here with us today. So Biosphere is still open, and Biosphere 2 is still open and alive. And actually, we've had a question in from Kelly that kind of speaks to this. You've told us some of the things that failed, but what did work really well, and what's the facility used now?
Yeah, and let me step in here. So. The word failure, I think, has really strong connotation, and we think experimentally about sort of major milestones that have happened scientifically. Oftentimes, those milestones come out of situations that were not anticipated or go against the hypothesis that was originally done, and so you could almost consider those to be failure. And so, Biosphere, even though that experiment didn't happen as they had planned it, there was a tremendous amount learned from that system, and so. That in and of itself, the creation of a one-of-a-kind Earth and environmental science laboratory like what we have with the facility is a remarkable achievement. And it's sort of their maiden voyage. We don't always get it right the first go-around, but it's remarkable that they got it done. So that was a big one. But I think we've done some remarkable experiments inside the facility. I'll touch on one with the rainforest, and I'll let Joaquin talk about the ocean one. But we know that the tropics are getting warmer and drier. We also think of them as a big sink for carbon dioxide that's we continue to see increasing in the Earth's atmosphere. But there's real questions as to how much can those systems absorb. So there were some models that folks had put out and said that today we're at 411 parts per million, and that when we reach carbon dioxide in the atmosphere, and once we reach a certain amount, these systems are going to saturate. And that amount that this model predicted was 600. So something we're going to reach in maybe 50 years, 60 years. So how do you test that? So you can't just put a dome over the tropics, whether you're in Africa or in South America. But here at Biosphere, you did that. And so we can help with model validation and calibration. So we subjected our system to those that the model laid out, and we were able to show that what our system and how it behaved match that of the model. It's saturated at 600 parts per million, which means rainforests do a great job at absorbing carbon up to a point, and then after that they saturate. That sponge cannot hold anymore.
So the point being that the benefits that those systems are offering us right now, there's a limit.
Yes.
And we now have a scientific hypothesis, demonstrated it within Biosphere 2 of what that limit is.
That's correct.
Well, one of the scariest things about global climate change is that the physiology of plants changes not only because of the temperature changes, but because of the CO2 concentration in the atmosphere. So the nutritional value, so the people that argue that global climate change isn't all that bad because CO2 is like a fertilizer. I mean, that's actually the word that they use, a fertilizer. So things will grow greener and happier and whatnot. And what John is saying is that that's only true for a point. But even before you get to that point, the nutritional value, for example, of rice drops by 25% in their protein value. So all this world that lives mostly on rice will get way less value of what they're eating as global climate change progresses. And the temperature changes are such. A few years ago, there was a terrible amount of corn that came out of the Midwestern U.S. because it was a really hot time. And it didn't matter how much water they were putting on the plants just could not actually operate very well. So the crop was a failure. So the temperature is a big deal, CO2 is a big deal for all kinds of reasons, including nutritional value of what you're eating. So, but going back to the other experiment, which probably is the most famous, just because oceans are sexy and corals are sexy, is in the 1900s.
I've not heard that before, that oceans and corals are sexy. But yeah.
It's true, and they're very beautiful, actually. But in the 90s, there was when the concentration of CO2 in the atmosphere was around 360 parts per million, an experiment was done at the Biosphere to increase it to 400, and at 400 parts per million, we killed the corals inside the ocean in the Biosphere. Right now, we're a little bit about 400 ppm, and the corals are taking a beating around the world. And we showed that that CO2 was sufficient to do it. But now they're even showing that the small variances in temperatures in the oceans are even worse than the CO2 variances, which drop the CO2 which drop the pH of the ocean. So the predictive value of what we can do at the Biosphere is a big deal. But I'd also like to point out that in addition to what we can do inside of the Biosphere is a think tank of things that we can do outside. And we have very strong programs on the relationship of energy, food, and water. And we have programs I mentioned yesterday in Mexico City now in trying to make the city more sustainable and through circular economy in the food. So there are various programs that we have in there that have to do with food, which aren't even done at the moment inside of the Biosphere. They're done.
I was going to ask a little bit about that because I guess it's great to know that it's helpful to know that we get to a certain CO2 level in the atmosphere and these are the effects.
Yeah.
I was wondering how has that been turned into action? I guess that's a big challenge of all kind of climate change related research. But are you working with organisations or individuals or how can that be translated into sort of some of the changes to avoid those effects that are demonstrated with the domes?
Yeah, it's a really big challenge, but we do try to bring resiliency to various places. Sadly, global climate change is a thing of social injustice. It's going to beat up on people that are poor more than the wealthy people, and it's going to beat up on places that are already deserts. So we have programs in partnership with Israel and in particular, actually, and these folks in southern Israel in the Negev desert have figured out how to grow plants out of rocks and salty water. It's the most incredible thing. So we have a lot of programs that we're bringing the best practices around the world. In northern Mexico, in the native lands of Arizona, where it's horrible. There's no water anymore. So yes, we do that throughout the world. But there's a variety of things that people have to think about deeply. One of them, and one of the reasons that the circular economy is so important to me, is that it's going to take a long time to ameliorate what's happening with global climate change. Because even if we stopped the production of CO2 on its tracks right now, the amount of CO2 doesn't disappear, right? So there's probably going to have to be some kind of engineering to suck CO2 out of the atmosphere if this whole place doesn't turn into a mess.
Which I guess is easier to do at Biosphere 2 than it is in the real Biosphere.
That's true. That's exactly right.
We're almost out of time. I think I always like to finish with a forward-looking question. What's next for you guys and the project?
Well, a lot of folks have looked at Biosphere and really referred to it as being ahead of its time. And today with the new research faculty, these younger research faculty that are coming into the field, they're really continuing to push Biosphere 2 into new directions. We've got really exciting projects taking shape in the rainforest, in our ocean system. We've constructed a massive experiment that looks at the fate of water in semi-arid environments. And it rains in the mountains, how much ends up downstream for you and I to use, and what impacts the quality. So we're continuing to repurpose and push the limits of Biosphere because, given today's political and economic climates, I think it's unlikely we're going to see the type of investment we saw with this facility into the future, unfortunately. So, this is a great opportunity to continue to repurpose it as new questions, as these new ideas, new questions, and new challenges we're faced with, and using Biosphere 2 in part to help solve them.
And I just want one very quick question from me, just because it's something I'm personally interested in, and I'm the host, so I get to hog the mic a bit. The question of soil and how little we know about that, and we often talk in the world of food that it all comes back down to soil really. Is that something that's being explored at Biosphere 2, or we're learning more about it?
Yeah. You know, we're in the era of the microbiome, and everybody talks about the microbiome in your stomach and your microbiome and how that changes the way you live. You know, including some mental issues now come from microbiome. Well, the same thing the same thing in soils. The microbiome is now becoming so important. Depending on the microbiome of soils, you can grow things better or worse. So there's an enormous amount of research of what controls the microbiome of the soils, and that's the kind of stuff we're doing at Biosphere.
Fantastic. And people can visit the facility, is that
Yes,
right?
and you're welcome.
Fantastic.
Bring the cameras.
If you want to come to Arizona or you're in the area, then it is possible to see this incredible feat of engineering and for yourself.
Yep.
Well, thank you so much, John and Joaquin, for your time today and for sharing what is an incredible story with us.